For example, letter B, we have sigma n equals 1 to infinity of negative 3 to the n x to the n over the square root of n plus 1. So again, what we're going to do here is to perform the ratio test rather. So that's limit n approaches infinity a sub n plus 1 over a sub n, and that's limit n approaches infinity of the original series shifted by n plus 1. So whenever we see the letter n, replace with n plus 1. That's negative 3 to the n plus 1 times x to the n plus 1 divided by the square root of n plus 1, which is n plus 2, times the reciprocal of the original series. Instead of dividing by the whole thing and creating a complex fraction, let's just multiply by the reciprocal. That's the square root of n plus 1 over negative 3 to the n times x to the n. Okay, so let's simplify this expression inside of the absolute value bar. So to begin with, we can break up this negative 3 to the n plus 1 as limit absolute value negative 3 to the n times the negative 3, and in this case x to the n plus 1, that's x to the n, x to the first, times square root of n plus 1 over negative 3 to the n, x to the n. So we can cancel out negative 3 to the n, negative 3 to the n, x to the n, and x to the n. I think that's about it, about cancellations. And we will be left with the following. That's going to be the limit as n approaches infinity of the absolute value of negative 3x times the square root of n plus 1 over the square root of n plus 2. Alright, okay, let's go one step at a time. So number one, I would like to take this negative 3 out of the absolute value bars and in front of the limit. However, because of the absolute value bars, this negative 3 will become a positive 3. Also, because the limit that we are computing is in terms of n, x technically is a constant which will be taken outside. But in this case, because x can be anything, we need to keep the absolute value bars. By x can be anything, I mean it could be positive or negative. So, and on the other hand, what I'm going to do here is to write this quotient of radicals as the radical of a quotient. Okay. And well, the next step is to compute the limit. So from the properties of limit, you might recall one from calculus 1, which states that when you have the limit of square root of square root of x, for example, this is the square root of the limit of x. In other words, we can introduce the limit symbol inside of the radical, which is what I'm going to do here. And also at this point, because well, this is a radical, it's in this case it's always going to be positive, so these absolute value bars are no longer needed. So let's see. So that's going to be 3 absolute value of x times the square root of the limit as n approaches infinity of n plus 1 over n plus 2. And what do we have? Polynomial over polynomial, both degrees are the same. Go with the ratio of the leading coefficients, which in this case are invisible ones. Alright, so in this case we're going to have 3 absolute value of x times the square root of 1, which is 3 absolute value of x times 1, which reduces to 3 absolute value of x. Alright, so that's the limit. But because we want to find the interval of convergence, we need to set it less than or equal to 1. I mean, just less than 1, not less than or equal, just less than, and solve the inequality. So this is 3 absolute value of x. I'm going to write it on the side. Divide both sides by 3. And set this as a compound inequality. X less than 1/3, but also greater than negative 1/3. Okay, by the definition of these compound inequalities. So let's see. So that means that so in this case, we could say that the interval of convergence is negative 1/3 to 1/3. However, it is to be determined whether these endpoints are both parentheses, maybe both brackets, or maybe one bracket, one parenthesis, or maybe one parenthesis and one bracket, just like before. How do we do that? How do we know that? So that we need to test the endpoints. So in this case, for the original series, test x equals the lower endpoint, negative 1/3. So sigma, okay, we write down the series. N equals 0, it's 1 actually. N equals 1 to infinity of negative 3 to the n times the negative 1/3 to the n power divided by the square root of n plus 1. Okay, let's write down the negative 1/3. Okay, and then from here let's simplify the series, and once we simplify it, well, we will be able to find a new test to determine the convergence or divergence. So we'll see. So this negative 1/3 to the n, so negative 1/3 to the n is the same as negative 1 or negative 1 to the n times, well, actually, you know what, instead I'm just going to write this 1 to the n and negative 3 to the n. I think it's easier to write it this way. Then 1 to the n is simply 1. Alright, so that's going to be negative 3 to the n times 1 over negative 3 to the n. The whole thing over the square root of n plus 1. And the good thing here is these two cancel out, leaving us with the following. Leaving us with sigma n equals 1 to infinity of 1 over the square root of n plus 1. So we need to look at this series, and we may have looked at a series like this before, and well, so we need to think of a test to determine the convergence or divergence of the series. And in this case, well, I'm thinking of a comparison test. Alright, could it be direct comparison or limit comparison? Well, we'll see. So compare with sigma n equals 1 to infinity of 1 over the square root of n. And what do we know about this series? This is the same as saying it's a divergent p-series, because, well, this can be rewritten the following way: 1 over n to the 1/2, with p equals to 1/2. So this is a divergent p-series. Alright, so we need to do the comparison test. So for divergence, well, if we did the direct comparison test, we would have to do the huge greater than or equal to big. Alright? However, is 1 over the square root of n plus 1 greater than or equal 1 over the square root of n? Well, unfortunately, this fails. So we cannot use the direct comparison. So we will have to find another, the plan B in this case. Remember, we had a plan B for whenever we are not able to determine huge greater than big or tiny less than small. So in this case, we are going to use the limit comparison test instead. So let's see. So we're going to find for the limit comparison test, we need limit of a sub n, that is the original problem, over b sub n, which is the test series. Recall, this is a sub n and this is b sub n. B sub n is the test series, a sub n is the problem series as n approaches infinity. And this is equal to limit n approaches infinity of 1 over square root of n plus 1 over 1 over the square root of n. And well, in this case, let's multiply by the reciprocal of 1 over n over the square root of n. That's limit square root of n over the square root of n plus 1, and approaches infinity. Alright? And well, the quotient of the radicals is the same as the radical of a quotient. And when again, I'm going to introduce the limit symbol inside of the radical. And this limit is 1. So that's the square root of 1, which is 1. And what do we have? Positive, finite. So because the limit is positive and finite, this series right here will do whatever we compared it with does, which in this case is to diverge. So that means that testing at x equals to -1/3, the lower endpoint, this will be for sure a parenthesis. Now the question is, will the other one be also parentheses, or will the other one be bracket? Well, we'll figure it out, but after we test the upper endpoint, which in this case is +1/3. Alright, so test x equals to 1/3. So after testing x equals to 1, x equals to 1/3, so 1/3, yes. So we get sigma n equals 1 to infinity of -3 to the n times 1/3 to the n over the square root of n plus 1. Where in this case, the next one will take a few more steps to simplify. So that's 1 to the n, which is 1, 3 to the n, which is 3 to the n. This is sigma n equals 1 to infinity. Okay, this one I'm gonna rewrite this -3 to the n as -1 to the n, 3 to the n. And this is 1 to the n, which is just 1, 3 to the n, over the square root of n plus 1. And in this case, 3 to the n, 3 to the n, and we will be left with the following, an alternating series, in fact, which is great. It's a shorter test. So that's the series that we need to test. And again, like we mentioned before, we test that by using the alternating series test. And for the alternating series test, we need to state the conditions that the limit a sub n equals to 0 as n approaches infinity. Okay, is that true? 1 over square root of n plus 1. And yes, indeed, at n equals infinity for large values, the denominator gets really big. 1 over big equals to 0. So the first condition is satisfied. Now let's check the second condition. And in this case, the second condition, a sub n plus 1, is that less than a sub n? I believe, well, actually it's b sub n, but either way, I mean, it's the same. So that's 1 over the square root of n plus 2. Is that less than 1 over the square root of n plus 1? Of course, in this case, it's true, because larger denominator on the left hand side is smaller than smaller denominator on the right hand side. All right, so this means converges. So converges right here, right? That means backtracking to the original power series that this is inclusive. So one parenthesis and one bracket. All right. So let's see. So that's the final answer. That's the interval of convergence for this power series. All right, let's have a look at another example, one more. What do we have? Sigma n equals 1 to infinity of n squared x plus 1 to the 2n, be careful with the 2n this time, divided by 2 to the n. So in this case, yes, I know on the previous exercises we did the ratio test, but can you use a different test? Like in this case, how about the root test? And actually the root test will be a lot better in this case, because think about if we do the ratio test. So if we do the ratio test, limit, that's an n plus 1 squared x plus 1 to the 2n plus 2 over 2 to the n plus 1. I think it would be a little bit more complicated if we deal with this one like this. So I think we should do instead the root test, and this is a good example, so you can see that you could use a different test, not just the ratio test. So the root test could be a lot shorter in certain circumstances like this one. So I'm going to use the root test instead. For the root test, recall that this is the limit as n approaches infinity of the nth root of the absolute value of the square root of the nth root of the absolute value of the given rule, which in this case is n squared times x plus 1 to the 2n over 2 to the n. Alright, so this means what are we gonna do here? Well, so number one, okay, so let's do one step at a time. So what I'm gonna do is I'm going to get rid of the absolute value bars in the first place, but notice this radical right here with index n that looks like a u. Okay, that's an n. We can split, well, that's the absolute value of the nth root of n squared. All right, and times the nth root of x plus 1 to the 2n divided by the nth root of 2 to the n. Okay, so oops. So from here, well, so let's simplify this. Okay, nth root of n squared is the same as saying limit of the nth root of n to the second power. And then in this case, the power n over here cancel with the index n. leaving us with simply x plus 1 squared, and with n here they both cancel, leaving us only with a 2 here. Now what about this n root of n? Well, in this case, this is a special limit. It's a special limit that we discussed in the ratio and the root test section in the previous chapter. You might recall that limit of the n root of n as n approaches infinity equals 1 is one of the limits that you can use on your notes on the exam, right? That you can you just use it. You don't, because otherwise you would have to go limit n to the 1 over n and then do the L'Hopital's rule, like treating it like an ln problem. And well, no, you don't have to do all this. It's fine. Just use these given limits. All right. So this limit equals to 1, and 1 squared is simple. It's simply 1. So limit n approaches infinity. So that's okay. I'm gonna take this 1/2 outside, and in this case, okay. So hold on. I'm gonna give me 1 second. Okay. So that's gonna be 1/2 limit. No, not limit. 1/2 absolute value of x plus 1 squared times the limit of 1. Well, actually yes. You know what? Let me leave it as n, just so you can see the consistency anyway with the limit process. And well, this limit is 1, so that's 1/2 absolute value of x plus 1 squared times 1, which is plus 1 squared. And well, in this case, because we want to check for convergence, we need to set this less than 1. All right. So now we need to deal with this inequality that I'm going to rewrite over here. Well, in this case, what about this? Well, so notice something. When this x plus 1, because x can be anything, we were supposed to have these absolute value bars. All right. However, this is squared, so we can simply 1/2 x plus 1 squared. All right. So let's try and solve the inequality and multiply both sides by 2 to get x plus 1 squared less than 2. And now we're going to solve this quadratic inequality, so we need to take the square root on both sides. Yep. And well, I know I'm missing the plus minus here, but I'm not going to write that plus minus, because in this case I'm going to be left with still the square root of 2. But recall that when we have the square root with a variable, this is the absolute value of x plus 1. And then from here, I'm going to set this x plus 1 less than the square root of 2, but greater than negative root of 2. And then subtracting 1 from the 3 sides of the inequality, we're going to get the following. Negative root of 2 minus 1. Okay, it's gonna look a bit complicated. Okay, yeah. Negative 1 minus root of 2 less than x less than that's negative 1 plus root of 2. And then from here we need to determine whether these are both parentheses, maybe both brackets, or maybe one parenthesis or one bracket. How do we know? Again, by testing the endpoints. And yes, these numbers look a little crazy, however, they're not as bad as they look, you'll see. So, test x equals the lower endpoint, which is negative 1 minus root of 2. Okay, let's do the testing. So that's sigma n equals 1 to infinity, and that's an n squared times negative 1 minus root of 2 plus 1 to the 2n divided by 2 to the n. And let's write down negative 1 minus root of 2 equals sigma n equals 1 to infinity n squared. So notice how these ones cancel. It's a different color for contrast. And we're going to be left with, well, actually, yeah, that's fine. So that's negative, be careful here, negative square root of 2 raised to the 2n over 2 to the n. Alright, so we need to be very careful when simplifying this quantity. One thing that you might want to recall before proceeding is this law of exponents. Whenever you have x to the m, and this is the same as saying x to the m to the n, or x to the n to the m, depending, and well, I mean, the order doesn't matter. Ultimately, what we're trying to say here is that power of another powers, the powers multiply, or when you have the product of two powers, you can write it back as the power of another power. Alright? And that's what I'm going to do with this negative root of 2 to the 2n. So, this will be sigma n equals 1 to infinity n squared, and okay, that's a negative root of 2 squared to the n power, to the n power. And in this case, what's going to happen? On the one hand, this negative will become positive because of the square, and the radical will cancel the square, leaving us with the following: sigma n equals 1 to infinity of n squared, and that's going to leave us with 2 to the n divided by 2 to the n. Okay, again, where is this 2 to the n coming from? Number one, the negative becomes positive, and then the radical cancel the square, leaving us with this 2 inside only, because this is raised to the n power, that becomes a 2 to the n. And again, see how these two guys cancel. Go away. And that's going to leave us with sigma n equals 1 to infinity of simply n squared. But come on, look at this series. So that's an n squared. So there's a couple of ways to look at the series. Number one, sigma n equals 1 to infinity n squared, we can use simply the n term test, for which the limit has to be not equal to 0 to show divergence. Let's see if it works. Limit n approaches infinity of 1n squared, and well, this is infinity, right? Because well, infinity squared, even more infinity, which is not equal to 0, which diverges. That's one way to see it. Another way to see it, I mean, it may not be the preferred way, but I mean, if you want to, like, I don't know, maybe explore other ways, feel free to do so, as long as the convergence or divergence criteria are still making sense. You can rewrite this as n to the negative 2, and then use a p-series with p equals to negative 2, which is less than 1, less than or equal to 1 actually, and it's also a divergent p-series. So either way is fine. So alright, so don't feel limited to use only one test. Feel free to open your mind and look at other possibilities. All right. The next, okay, coming back to the original series, okay, because to the lower endpoint of x equals -1 minus root of 2 diverged, well, this one is parentheses. Let's see if the upper endpoint is parentheses or bracket. Let's figure that out. So, test x equals to -1 plus the square root of 2. So sigma n equals 1 to infinity, and that's on n squared, -1 plus root of 2 plus 1 to the 2n over 2 to the n. So -1 plus root of 2, cancel the ones, we are left n equals 1 to infinity, n squared times the square root of 2 to the 2n. All right, and in a very, very similar way, I'm going to rewrite this root of 2 as well, square root of 2 squared to the n, and see how the radical cancels the square. Radical cancels the square. So that's sigma to the n over 2 to the n. All right, and again, check this out. These two cancel. Oops, that's not 2 to the second, it's actually 2 to the n. Cancel, cancel, and we're left with sigma n equals 1 to infinity of n squared. But wait a minute, isn't it the same series that we got before? Do we really have to do again the test? No, for the same criteria, diverges. All right, no need to do it again. And that means that's also parentheses. All right, so for the next example, so what do we have? For letter D, n factorial x to the n. So I'm gonna let you try this one, and once you're done, so how about try letter D and letter E and see what you get. And if you want to see the solution, check the next video.